So yes, this is the title of my talk, and actually I will be talking about two different projects, very related, that we have been doing in Milan in the last couple of years. And the topic is somehow quantum batteries, or at least what I mean with quantum batteries. So we started with very generic definitions, an introduction to this field. What is a quantum battery for me is just a temporary energy storing device whose charging and discharging processes are described by the law of quantum mechanics. I think that the first time it has been used was in this paper by Abhishek and Fan. Then from there, there's been a lot of research and works on this topic. There is also this nice review of modern physics. If you're interested in the topic, there are a lot of details about that. And why is it interesting to study quantum batteries? And what I like is that I think it's very similar to, in general, to the field of quantum information or quantum technologies. And to use the same words that was used by Bauer last week, we can do this for pleasure or for profit with a different meaning here, but related to what you were saying last week. But yes, there are fundamental reasons. So you want to study the ultimate limit posed by quantum mechanics on this kind of processes, on work extraction and charging of quantum batteries. But then there are also so-called technological reasons. At least now there are some theoretical papers showing there should be a quantum advantage if you use quantum mechanics in the charging of quantum batteries. Then you can talk about this advantage. Advantage could be because of quantum or collective effects. There is some debate or research about this, and there are also some first example of experimental papers. So now let's introduce the figures of merit we will be talking about. So we are talking about work extraction, energy extraction. So the first thing we have to introduce is the Hamiltonian of the system. And then we assume that we have prepared our system in a certain quantum state ρ. So we know that we can then define the average energy of our system as the trace of ρ h naught. Then we can define how much work we can extract from ρ. We will use, there are many different definitions of work for quantum systems. So here we will use probably the easiest one. We assume that if we implement a unity operation on ρ, the average extracted work will be the difference between the energy of the state before minus the energy of the state after the unitary operation. Then you can ask yourself another question, okay, this extracted work will depend on the unitary operation I've implemented. What if I try to maximize overall the possible unitaries? And doing this, I will define a new quantity, which I call it, I didn't call it, but people call it ergotropy, so which is exactly the maximization of this extracted work over all the possible unitaries. This was introduced the first time in this paper by Alaverdian and collaborators in 2004. Actually, it's a very nice paper with a lot of discussions and results. And one of these results is also showing that you can actually write an analytical formula for this ergotropy in terms of eigenvalues and eigenvectors of the Hamiltonian and of the quantum state you start with. Okay, some properties of the ergotropy. So ergotropy is always greater than or equal than 0, and of course, from the definition, is upper bounded by the energy of the quantum state. Then this allows you also to define a class of states, that is the class of passive states, which are all the states that have 0 ergotropy. You can also fully characterize them mathematically. These are states that are diagonal in the energy eigenbasis and such that you don't have energy inversion. So the eigenvalues should satisfy this property. Of course, Gibbs states are the easiest example of passive states, but one result is that not all passive states are Gibbs states, unless you are in a qubit system or in a continuous variable Gaussian systems. Then another easy property is that the ergotropy of pure states is equal to the energy, so you achieve the upper bound. And again, the mathematical reason behind that is quite simple. You know that in a finite dimensional quantum in Hilbert space, all the pure states are unitarily equivalent. So if you start with a pure state, you can always find a unitary that sends you to the ground state of the Hamiltonian. And then another property you can prove is the convexity of the ergotropy. So the ergotropy of mixture of quantum states is always upper bounded by the average of the ergotropies of these states. Okay, Now I want to introduce a new concept, demonic ergotropy, that was actually introduced in this paper by Franchik and collaborators in 2017. Now we have two parties, so we have a bipartite quantum system, a bipartite quantum state, and we have the system S here and the auxiliary system A. They may share classical or quantum correlation, and I want to extract work only from the system S. And okay, now let's assume that we don't have access to the auxiliary system. We ask ourselves, okay, what is the maximum extractable work I can have? And naively, I mean, trivially, in this case, you have that the maximum extractable work is the ergotropy of the reduced state. So I take the partial trace over A of the bipartite state, I calculate this state, I calculate the ergotropy, and this is the maximum amount of work I can get. Now let's assume we have some access to the auxiliary system. In particular, we can perform a POVM here. And then you ask yourself, okay, what is in this case the maximum extractable work? Then we know that if we measure here, we will have some conditional states of the system with a certain probability. So from each conditional state, we can extract a different amount of work, and then the maximum extractable work will be the average of the ergotropy of the conditional states. And this quantity we call this quantity demonic ergotropy. Then we know quantum mechanics. We know that in quantum mechanics, tracing out is actually equivalent to measure and forget. So we can always write the reduced state, the partial trace as a mixture of conditional states for any given POVM on the auxiliary system. We know, we said before, that the ergotropy is a convex quantity. And because of that, now we can write that this demonic ergotropy is always greater than or equal to the ergotropy of the reduced state. So mathematically, okay, this was due to the convexity of the ergotropy, but physically or informationally, we can understand this result by assuming, by thinking that we have here a Maxwell demon that is getting some information on S thanks to this measurement on A, and then it can use this information to optimize the unitary U that was in the definition of the ergotropy before. So by changing the unitary depending on the result A, it can extract more work from each conditional state, and then it gets this kind of enhancement. Okay, I just want to mention that you can actually generalize this framework also to the situation where you have an additional thermal bath with at a certain temperature T, and then you can use also this bath as a resource to extract more work, and you can define this demonic work, and also in this case you have, of course, that you can increase the amount of work thanks to this measurement on an auxiliary system. This was done by Gonzalo and collaborators 1 year later in this nice PRL. Okay, some properties of the demonic ergotropy. We just proved that the demonic ergotropy is always greater than or equal to the ergotropy of the reduced state, but it's still, of course, upper bounded by the energy of the reduced state. Then, now, if your system and the auxiliary system are in a pure state at the beginning, before the measurement, and then if you apply a POVM formed by just rank 1 projectors, then you know that in this case, the conditional states will still be pure, and then with just few one-line calculation, you obtain that the ergotropy, the demonic ergotropy is actually equal to the upper bound, so to the energy of the reduced state, and this is independent on the POVM. So this result, so you get the upper bound for any POVM that satisfies this property of rank 1 projectors. Of course, you have something different if the conditional state are mixed, then the demonic ergotropy will depend actually on the particular measurement you perform on A. Okay, so let's now change a little bit topic. Actually, I probably don't need all these slides. You have seen this many times in this couple of weeks. So I want to talk about open quantum system and continuously monitor open quantum systems. So we have a system interacts with a Markovian environment. So you can phrase this in terms of a train of input modes that interact with the system, then they leave, you have some output. And then if you don't measure, we have seen also in the last lecture that you get the master equation in the Lindblad form. But then what happens if I put a detector here And so the output modes, the environment is continuously monitored. We know we have an unraveling of the previous master equation. You have quantum trajectories, the title of this program. And all these quantum trajectories will depend on the outcomes of this detector and actually on the kind of detector we have. Again, we have quantum jumps. So we have Poisson increment here, and this will be the output, and this is the stochastic master equation. We can have homodyne, and this will be our photocurrent, and this will be our diffusive stochastic master equation. And again, if we know that if we average the stochastic master equations over all the possible trajectories, we get the Markovian master equation. Just a slide of self-promotion here. I've been working on this kind of things for a while now, in particular quantum metrology. I'm not talking about quantum metrology now, but since I'm around for a few days, if you want to talk about these topics, I will be happy to talk about this. But let's go back now to our quantum batteries. And now we talk about open quantum batteries. And again, the definition is quite trivial. An open quantum batteries is just a quantum energy storing device where the quantum system that acts as a quantum battery interacts with an environment and then undergoes decoherence and dissipation. And okay, probably you know where I'm going. What happens now if I can monitor the environment? So I can put the detector here at the output, and we've just seen we have trajectories, and depending on the detector and so on, and these detectors form an unraveling of our unconditional state. And so we can define a demonic ergotropy corresponding to the unraveling, and of course also to the efficiency of our detector. Here will be an important parameter in the following. And because of the property of the demonic ergotropy, so the convexity property, again, we will have a demonic enhancement here. So this demonic ergotropy will be always greater than or equal to the ergotropy of the unconditional state, the one evolving according to the Markovian master equation. And again, the interpretation is quite simple. We have a Maxwell daemon here that gets information on our trajectory, and then it can use this information to optimize the work extraction unitary and extract more work on average. Okay, some properties of this unraveling demonic ergotropy. So we just want to translate the previous properties to the open quantum system scenario. We just proved that is lower bounded by the ergotropy of the unconditional state, is upper bounded by the energy of the unconditional state. And when do we get this upper bound in this case? We get it if you start our dynamics with an initial pure quantum state, and if we have a measurement of the environment with unit efficiency. So if eta, the efficiency parameter, is equal to 1, then we know that in this case the evolution will be described by stochastic Schrödinger equations. So each trajectory will be in a pure state, and for the same reason we showed before, then this demonic ergotropy will be equal to the energy of the unconditional state. And again, I think it's important to remind ourselves that this is true independently on the unraveling. So if we do photodetection, homodyne, heterodyne detection, you will always get this result, of course, with efficiency equal to 1. Then probably the most interesting question is then what happens for mixed states unraveling? So what happens if you, for example, you have non-unit efficiency monitoring, or if you have initial mixed states? And in this case, which unraveling, the question is which unraveling is more efficient for a quantum battery to charge and extract more energy from a quantum battery? And we don't have a definitive answer to this question, but what we tried is to study this problem in the most simple and paradigmatic example of a quantum battery, probably not the most useful example of a battery, but would be a qubit, so a two-level atom, and where your charger is classical driving, so this atom is driven by a laser with amplitude alpha, and then we assume that there is some spontaneous emission, fluorescence. So we have seen that the unconditional master equation in this case will be the following. This will be the driving rabbit term, and this will be the spontaneous emission. And then we assume that you can put a detector here, and this can do in principle photo counting, homodyne, or heterodyne with a certain finite efficiency eta. And we want now to answer to the previous question. So which is the best unraveling if you have a mixed state unraveling? So this is the result. I mean, one of the results we are plotting here the demonic ergotropy as a function of time. And okay, let's start from the black and the gray line. So this black line is the lower bound, so the ergotropy of the unconditional state, and this is the upper bound, so the energy of the unconditional state is what you would get if you have efficiency equal to 1 for your detection. And this corresponds to either homodyne of sigma x, sigma y, heterodyne, or photodetection. And then what we obtain is that homodyne for a certain quadrature, so the one that gets information on sigma x and heterodyne are the best unravelings. The other homodyne is a little bit not as efficient, and photodetection is the least efficient unraveling. To be honest, if you ask me why I get this result, an interpretation of this result, I don't know. For example, I would have expected that the heterodyne would have been between or better or between the two homodynes, so I don't really understand this result. For photodetection, we have a kind of certain interpretation, so the fact that every time you have a quantum jump, then your two-level atom will always get back to the ground state, and yes? In sigma x. Yeah, I mean, of course, that there is some asymmetry between these two homodyne. This is something I would have expected. But why heterodyne is as good as sigma x, that's something I almost, yes, but I would expect in between, you know? Yeah, I don't know. That's what I was expecting. Yeah, and for the photodetection, the reason I have is that you always get back to the ground state, so you have to start again the charging from scratch every time you have a quantum jump. And we have to also remind ourselves that for eta equal to 1, they all go up here. So all the interpretations have to hold just for eta smaller than 1. And as long as eta goes to 1, all this kind of interpretations don't hold anymore. So that's another issue. And yeah, we have another plot, but there is no much more information here about what happens at steady state as a function of alpha over kappa, so the ratio between the driving and the amplitude damping parameter. Again, you get basically the same kind of results. Then again, you have something less, more interesting in the other scenario where you start with a mixed state, and you monitor with eta equal to 1. Again, in the transient here, you still have a mixed state unraveling. Then along times, you will basically purify all the trajectories. So you see all the lines will get basically to the upper bound, to the energy of the unconditional state. But in the transient, you have something different, and you have this kind of nice result that tells you that basically at small times, the homodyne and heterodyne strategies are able to purify the system such that you have a sharp increase of the ergotropy. So I just want to remind ourselves that this means that we have some energy in the initial state, but this energy cannot be extracted unitarily. But as soon as you do some homodyne and heterodyne measurement, then this energy becomes almost immediately available for work extraction. Then you have, again, a transient where this goes down. And I just want to compare also with this dotted line. This corresponds to the upper bound in the previous case where you start with the ground state. I didn't mention this before. And this means that basically if you start with a passive state with some energy, in the transient it's better this situation than when you start with a pure state and you monitor with efficiency equal to 1. It's a little bit complicated to explain, but I don't know. I hope you got my point. Okay, so these were the main result about our paper. So we generalized this concept of demonic ergotropy to unraveling, and then we studied for this particular case of a qubit, a two-level atom with spontaneous emission. Let me talk now about the second work, which is kind of related, where the goal of this work is to have experimental, I don't know if I should call it verification, we are probably in the paper, we call it simulation of demonic work extraction on a digital quantum computer. So let me explain what I mean with this by actually starting again with some theory and introducing collisional models or collision models. So these have actually been already introduced last week in the talk by Alexia of FEV. Collision model are a versatile and efficient tool to describe open quantum systems, where basically you discretize both time and the environment. And in particular, you can also put your Markovian assumptions, which is very similar to what also was shown in the previous lecture by Nina. And so you have your input state that interacts sequentially with some auxiliary systems. And in the Markovian assumption, these auxiliary systems do not interact with each other, are initially uncorrelated, and each auxiliary system interacts just once with your input state. So after n steps, you trace out all these auxiliary systems, and you get your output state. And this kind of simulate the open quantum system dynamics. Yeah, actually, if you choose properly this interaction Hamiltonian, the state of the system here, and you take in a proper way the infinitesimal limit of the time step, you can really reobtain the Markovian master equation we were talking before. So for this unitary, with this Hamiltonian, you exactly obtain the Markovian master equation with Rabi driving and spontaneous emission. Okay, so what now if instead of tracing out this auxiliary system, we put some detectors here? And of course, we have now a string of measurement outcomes, A1, A2, and AN, and this A1, A2, AN define a conditional evolution for your system, so a quantum trajectory for your system. So this is what people call continuously monitored collision models, and this actually, I think, was introduced in the first time by Gabriel Landi and collaborators in this paper, but actually is very related to what we have been talking about in these weeks on quantum trajectories. Also in the continuous time, you can really reobtain the stochastic master equation by really studying this collision model. This is the way I teach my students the derivation of stochastic master equations, and this is also similar to what also was shown in the previous lecture, at least in one of the derivations. And okay, let's talk about extractable work. We are talking again about the same thing we were saying before. Now we have a daemon here that takes these outcomes, A1, A2, and AN, and now we can choose extraction unitary that will depend on these outcomes in order to send this state to the corresponding passive state. And you can optimize, of course, this unitary depending on this, and you can define the Daemonic extracted work, and you can write it again by using this formula. Is the difference between the energy of the unconditional state, so basically the state you get here, minus the average energy of the conditional states after the extraction unitary. And of course, if you choose these unitaries as the optimal ones, this will be equal to the Daemonic ergotropy. Now, the question we ask ourselves is, can we implement this continuously monitored collision model and demonstrate this or simulate this Daemonic extraction protocol on a digital quantum computer? And the answer is yes, as we will see in a minute. Again, as I said before, we can define these unitaries on, and okay, we are going to talk about IBM quantum computer and Qiskit, and as you probably know, you can easily implement at least tell the quantum computer to implement these gates. And then now with the dynamic circuits, you can also perform mid-circuit measurements and feedback, or you can call it feed-forward, feedback operations. So you can do this kind of reasoning. And this is basically an example of a two-step continuously monitored collision model with Qiskit. This is what the circuit looks like for the case of n equal to 2, so for 2 steps. So you start with, you just need 2 qubits and a classical register. You start with a battery qubit and the auxiliary system qubit. You make them interact with this unitary. Then we perform this sigma x measurement on the auxiliary system qubit, so Hadamard and sigma z measurement. Then we reinitialize the auxiliary system qubit, and we do it again. In the meanwhile, on this classical register, we get all these outcomes. So for n steps, we will have 2 to the n possible string of outcomes, and so 2 to the n possible trajectories, and then Qiskit allows you to do this which case function. So depending on which trajectory is defined by these outcomes, you can apply a different unitary. And okay, I think, and then at the end, you can perform a sigma z measurement on the battery in order to evaluate, to estimate the energy after the extraction unitary. So there is a small caveat, is the fact that this is actually because of the interface you have with IBM quantum computer right now. So the point is that you have to store in advance these possible unitary operations. So you have to simulate your collision model in advance, so that you get the optimal unitary for all the possible 2 to the n trajectories. So this doesn't scale very well if you increase n too much. And but again, this is not related to the concept itself. It's just about that you cannot do. You cannot update also. You cannot compute this unitary in real time in Qiskit. And but apart from this, then you can run this circuit many times, and this allows you basically to calculate this term that is one of the 2 terms you needed to calculate the demonic extracted work, because by repeating this experiment many times, you are sampling both on this average energy of the conditional states and on the probability of each trajectory. Then you can run a very more simple circuit without the measurements to estimate the unconditional energy of the output of your collision model. So you get this, and so you can have an estimate. I mean, you can calculate the value of your demonic extracted work in your experiment. And yeah, these are the results. I mean, the first results we got. You have 3 lines. The red and the green line are theoretical values. They correspond to, the red line corresponds to the demonic ergotropy in theory in the noiseless model. So actually this corresponds to the energy of the unconditional state in the noiseless model. And the green line is the demonic, is the unconditional ergotropy. So the ergotropy of the unconditional state, again, in the noiseless model. Again, I said noiseless, but you'd probably asking why I said noiseless. You will see in a minute. And the black lines are actually the experimental results we got from IBM. And okay, so we were already quite happy about this, because we saw that we could really implement a continuously monitored collision model with feedback on IBM quantum computer, and thanks to this, we were able also to prove a demonic enhancement, a demonic work extraction, because these points are always larger than the green ones, so we actually get some enhancement. But as you can see in both cases, so these are for alpha equal to kappa equal to 1, this is for a larger value of kappa. In both cases, there is a gap between the black lines, the black points and the red points. And the reason is, of course, why you have this gap, of course, because these values, the red ones, are obtained assuming that you have no noise in your collision model, so no noise in your quantum computer, but IBM quantum computers are noisy. We also learned this morning by Kirillo. And so the good thing about IBM quantum platform is that also they give you some information about the noise affecting your qubits, so you can get the coherence times, readout times, and this allows us also to build a noisy model of our experiment, also a kind of quite easy noisy model. So by using this information, we can now consider this noisy model instead of this noiseless model, where basically during the measurement of the auxiliary system, the battery qubit undergoes some amplitude damping and dephasing channel. Then we can model also some noise in the sigma z measurement. And why do we need that? We need this for 2 purposes. On the one hand, we can now run a simulation of this circuit by using QTIP or whatever you like to calculate the new values of the demonic ergotropy that won't be now equal to the energy of the unconditional state, will be smaller because of noise. But more importantly, we can also run a simulation of this model to obtain the different outcome quantum trajectories here, and then find new unitaries that actually optimize the work extraction for these quantum trajectories that are different from the ones in the noiseless model. So we can also improve the work extraction part of the protocol by using this information. So these are now the new results. We have two more lines in the plots. So the pink one is again our theory values. So these correspond to the demonic ergotropy for the noisy model. So you see that this is now below the red. These are now below the red points. And the orange lines are now experimental results where you now implement the optimal unitaries according to the noisy model. Okay, let's now focus on alpha equal to kappa equal to 1. So what does tell us in this plot? This plot is telling us that already with the previous unitaries, so with the black lines, we were already doing our best. So because basically the black lines are very near to the pink ones, so we could not extract more work from those trajectories. And in this other plot, we have also something even better, because not only the pink line is below the red line, but we have this non-negligible gap between the black and the orange. So now the unitaries are very different, and by using these new unitaries, we were able basically to close the gap between the black and the pink line. Of course, as you can see, when you go above 6 steps of your collision model, the protocol doesn't work so well, and this is probably because our model is too simple to take into account all the noise that are playing role in the IBM quantum computer. So, okay, I think that's almost it. So these are the conclusions. We extended the concept of demonic ergotropy to open quantum systems, and we have shown also a simplest example of a monitoring enhanced open quantum battery, and observe this hierarchy between different arrivalings for final detection efficiency. And then we have shown a proof of principle simulation of demonic work extraction on IBM quantum computer. Now we are still working on this. In particular, we would like to design other monitoring and feedback enhanced strategies for more complex quantum batteries, for example, when you have so-called Dickey quantum batteries. And also we would like to understand a little bit more about the relationship between this demonic ergotropy and second law of thermodynamics, cost of measurements, and so on. So finally, let me acknowledge the people who were involved in this work. Daniele Morrone, who has actually just finished his PhD with me in Milan. I should change this affiliation, now is in Palermo. And Navid Eliasi, who was a master student at the University of Kurdistan. Again, I have to change this affiliation as well, as he's now a PhD student in Chalmers University in Sweden, and my long-standing collaborator, Matteo Rossi. Thank you.
Questions? Has anyone got the microphone?
Okay, it's really interesting talk. Thank you for the nice one. I have a question about how you actually do the, what is that called? Like search for the U that actually optimize the energy. I think it's a lot, right? You have to search for the...
well, actually, it's not that difficult, because once you have, at least on paper, once you have your quantum state raw, then you already know what is the passive state, and you can write on paper what is the optimal unitary sending the state to the corresponding passive state. So it's actually something, for a qubit, it's kind of, I wouldn't say trivial, but it takes just a little bit. But there is a constructive way to write this unitary for any quantum state rho.
Oh.
Yes. Yes, it's a function of the state. The state is a function of the measurement outcomes, and so in some sense is deterministic. It's definitely deterministic. Yeah. No, for any. Yeah.
Okay. So I have a question / comment. Maybe if you could go back to one of the graphs from the first part of the talk, the time-dependent one. Yeah, that'll do. Okay. So this is the ergotropy at any time.
Yeah.
But it seems to me if you're doing a quantum trajectory unraveling, you could choose the time to stop and extract the work from the system.
Yes.
And in that case, it seems to me that you would not actually necessarily be upper bounded by the master equation solution, or let's say not even necessarily upper bounded by the peak of the master equation solution.
Why? Okay, each time, I don't know if I got your question.
Because I guess, well, we can talk about it afterwards.
Sure.
But I guess because at any given time there will be a spread, and some states will have more energy and some will have less.
Okay. So this is actually, probably I got your question. So if you use your time t as a closed loop control variable, so you can think about this. So that's what you were thinking.
Primitive sort of control.
Yeah. So that's what we are actually looking for, and we are just started this to look into that, because let me understand if I understood your question properly. So if I know that one of my trajectories is already above a certain threshold, I can stop there. Yeah, then definitely I totally agree with you, and we are actually looking into that. So this actually will eventually depend on the moments of the Daemonic ergotropy. If basically the distribution of the ergotropy of the trajectories, and then you can look also at the moments, and then maybe if at some time you have the distribution is more, it's not about the average value, but it's more about the other moments. So maybe you have more trajectories that are have a larger value of ergotropy, and then in that case, you expect that you will increase your outcome.
And in that case, even for the case of perfectly efficient unraveling, you could see a difference between different unraveling.
I think so. Yes. I think you're right also about this. I didn't think about that, but yes.
Right.
Yes.
Okay. Any other comments or questions? Okay, if not, let's thank Marco, and brings the day to an end. See you all tomorrow.